Hello everyone, this is Brenna, your friendly 121LA, and today I'm here with a problem about heat and heat transfer and things like that. So this is on the chapter of heat, Q equals mc delta T, things like that. So this problem says, you're bicycling at a good clip using 400 watts of metabolic power. As you exercise, your body will start to warm up, and you will perspire to keep yourself cool. So A says, if your body is 25% efficient while cycling, how many joules per second of thermal energy will your body gain if you have no means of exhausting excess thermal energy? And then B says, assume that the only means by which your body cools itself is evaporation. To keep your body temperature constant, what mass of water must be evaporated during a 1-hour ride? What volume of water must you drink each hour to keep from becoming dehydrated? So, and it says 1 kilogram of water has a volume of 1 liter. Alright, so let's go ahead and start with A. So A says that our body is 25% efficient. Okay, so we know that mammals are 25% efficient, and it wants to know how many joules per second of thermal energy will your body gain if you have no means of exhausting excess thermal energy. So we're looking for the thermal energy per second. We want to know what that is. We know that the metabolic power, or the PMET, is equal to 400 watts. Okay, if we're saying that our time is equal to 1 second and our power is 400 watts, then that means that our metabolic energy, or our chemical energy, delta E chem, is equal to 400 joules per second, right? Okay, well, we know that humans are only 25% efficient. If they're only 25% efficient, then that means that we're going to have to take this number and we're going to have to multiply it by something, right? If 25% of the energy is going into doing something useful, is going into doing work to move this air, then that must mean that 75% of it goes somewhere else, and that somewhere else is thermal. So I'm going to find how much thermal energy there is by finding 75% of 400, which we know is just equal to 300 joules per second, and that is going to be equal to that thermal energy per second. Okay, so we just found out how much thermal energy we gain when we do this. B says, assume that the only means by which to keep your body cool is evaporation. To keep your body temperature constant, what mass of water must be evaporated during a 1-hour ride? Okay, so we know that we have a time of 1 hour, and we're looking for the mass of water during that 1 hour. Mass of water lost. Okay, well, I want to think about how exactly this water is lost. So if I'm bicycling, let me go ahead and draw a bike here. Here's the handlebars and the seat, we'll say. Here's the bike tires. That's beautiful. That's about how it looks, okay? There's the pedals. This is awful. Anyway, we're not going to worry about that. If we're biking along at some speed, we are losing water to evaporation. So water in our body, which is liquid water, H2O, liquid, is being turned into gaseous water, right? It's being turned into water vapor. Oh, okay. This process here is called evaporation, and we can find the thermal energy lost to evaporation by a specific equation that we've learned about. And that equation is just Q equals the mass of the water times the latent heat of vaporization. But we're not looking at heat, we're looking at thermal energy. Because we're talking about the body here, right? The body isn't transferring heat anywhere. It's keeping thermal energy within itself to heat up this water, and thus it evaporates. And that's how we keep cool. So ultimately, we end up with an equation that looks like this. The thermal energy is equal to the mass of the water in kilograms times the latent heat of vaporization for perspiration. Okay, so now I want to see what that latent heat of vaporization is for perspiration. And Brian sent it to me. It is, LV is equal to 24 times 10 to the 5th joules per kilogram. Okay, so we know that much. Now we need to find just the true thermal energy. We know that the thermal energy per second is equal to 300 joules per second. But if we're going for an hour, we need to incorporate that time, right? Basically what we have here is just the power, right? The power of the thermal energy lost or absorbed. So in order to get rid of that seconds unit, we need to convert 1 hour into seconds. So let's go ahead and do that. In 1 hour, there are 60 minutes, and in each minute, there are 60 seconds. So there are 3,600 seconds in 1 hour. Okay, so if we go ahead and do that, we get a power that is equal to, let's see, a big number. Not a power. We get an energy that is equal to 1.08 times 10 to the 10 to the 6th joules. And let me go ahead and move this down. Now that we have our energy, we can go ahead and solve this equation, right? Because we have everything except for the mass of the water. So if we go ahead and do that, 1.08 times 10 to the 6th joules is equal to the mass of the water times the latent heat of vaporization for perspiration, 24 times 10 to the 5th joules per kilogram. We can go ahead and divide that 1.08 times 10 to the 6th by the latent heat of vaporization for perspiration. So let's go ahead and do that. 10 to the 5th. And we end up getting a mass of water lost that is equal to 0.45 kilograms, which is about equal to half a kilogram. So that's the mass of water we lost, but ultimately asked what volume of water do you need to drink every hour to stay hydrated? You're losing a half a kilogram of water every hour, right? And if 1 kilogram of water, H2O, is equal to 1 liter, then every hour you have to drink a half of liter of water, H2O, every hour. And that is the water that you need to stay hydrated. And I would say, I mean, you could compare this, you could look up how many liters are in a gallon, so maybe we'll do that just to compare this. We'll say liters to gallon, and I'm just using Google for this. So if I say I have half a liter of water, hold on, 0.5, that is equal to, let's see here, half a liter is about equal to 0.13 gallons of water. So about 1/10 of a gallon, and I'm not sure what that is in cups, but you would have to go 10 hours to drink 1 gallon of water. And I would say that seems pretty reasonable. You know, I generally don't drink a gallon of water in a day, even when I'm doing something super active. So I would say, yeah, for a well-trained cyclist, going this fast, using this much power, I would say, yeah, this answer makes sense, because, you know, it would take 10 hours to drink 1 gallon of water. That seems pretty reasonable to me. Alright, I think that is all for this one. Sorry for my dog barking in the back. She's super annoying. Her name is JoJo. But you can hear her in the next one.